Hello and welcome back to another exercise. In this lecture, we're going to go ahead and do some seismic design, earthquake design. So we're going to, let me bring in my Revit model right here. Okay, we got this 5-story building and with a 20-inch by 20-inch concrete column. And we're going to do some seismic design on this. Actually, let me go to the PowerPoint itself too. There it is. So we're going to go ahead and calculate the base shear and vertical distribution seismic force for this 5-story building. The criteria for this building is located in Berkeley, California. In your assignment, you're going to be Boston. And the first story is 12 feet. The rest of them are typically 10 feet and 9-inch thick concrete slab on all floor with the regular weight concrete, 150 pound. Also assume the superimposed dead load of 30 pound per square foot on all floor and 10 pound per square foot on the roof. A glass curtain wall system is used for all for the facade and of the building, which has about 8 pound per square foot. We're going to use the structural force resistance system consists of moment resisting frame in both direction, and the site is a class D. I'm just going to show you a couple of my PowerPoint here. This PowerPoint is about over 100 slides, so we basically want to go ahead and go to the ASCE 722, look at these two area, seismic base shear and vertical distribution of the seismic force, and we calculate the force for each floor, and then we have our force for the design load for earthquake. What else I was going to show you, one of the first thing we got to do is right here. Find out the seismic design category, and there's about 6 of them, and based on this table we're going to find out which category this area is going to fall into. Okay, let's get to work. Step 1, we want to go ahead and calculate the SDS, and let's go to start up your Excel. I'm going to go ahead and start the Excel right there. To get some of these information, I think you want to go to, let's go to ASCE hazard. In here, type in the location, ASCE hazard tool, type in the location, Berkeley, California, right there. And then we want to go ahead, risk category, we'll find it later, but I'm just going to put in 2 here for now. And then we want to go to tornado, flood, snow, seismic. Click seismic, and we're going to be in default site classification. Let's go to D, and this was given, and this is what we figured out. Let's view result. Okay, let's look at the summary. Okay, here's some of the stuff we would like right here. So I'm going to copy all these over to my spreadsheet. So we can see right here, actually, they already figured out the seismic design category E. That's what we're looking for. But also we write down all these value, and I copied this all over here and put it on my spreadsheet. So our size, we are in a SDS E. Okay, we're going to move into step number 2, which we're going to calculate the response modification coefficient R, and that's from ASCE 722 table 12.2-1. Let's go there, see if we can find that. So we're going to look at 12.2, keep going up. This is the table. On the top, right, we have a seismic force resistance system. That's your SFRS. And then we have what section you gotta look at into it. That's pretty good. Respond, that's what we're looking for right here. And also you can find all these too. And we know our category is category E. So our thing was, it wasn't bearing wall, it wasn't that. It was moment resisting frame system. That's what it was. And it was concrete. So it's right there, number 5. Special reinforced concrete moment resistant frame. So if you come up, our is 8. Our R is equal 8. And keep an eye on these right here. And NL, that's good, no limit. So NL stands for no limit. So we're gonna go into write this. This is it, 8. We're looking for. Let me close this out, go back to the writing. So from there we said, okay, our R is equal 8, and also no limit on height. No limit on height. That was the NL stand for, right, what we saw. All right, let's move into step number 3. Okay, so we're going to find IE, and our rest category IE is equal 1, and that comes from ASCE table 1.5.2. This is easy to find. You already know this because we did the wind design, so I'm not going to go over this step. And you can find it from that table. Okay, we're going to go to step number 4. Step number 4 is calculating the period of the structure T. And if we go to ASCE 12.8.21, this is the equation we want to use. Let's go there anyway. Let me get that on here. And this is our step number 4, appropriate fundamental period. And it's a good reading. You should read this. And TA is equal to CT times HNX. And CT is given from table 12.82, which we're going to go. Also, X is given from the same table. And HN is the height of our building. So let's go to table 12A2. I want to know what CT and X are. 12A2, keep going. That's it right here. So we're going to look for a moment resisting, concrete moment resisting frame right there, right here, this one. And if we go across, CT is 0.016, write that number down, and X is 0.9. All right, let's go and calculate that. So TA is equal, CT was 0.016 times the height of our building is 52, and by power 0.9, and that comes out to be 0.56 second. Okay, that step is done. Okay, step number 5, we're going to go ahead and calculate the or find out the long period T transition TL. If we go into ASCE figures 22, which I'm not going to go, or we can go to hazard tool, we can find TL. So let's go to the hazard tool. We were there beginning, remember? Bring this up right here. And if we go here, we were there before. TL is right there, is equal 8 seconds. So I'm going to write that down. Okay. TL is equal 8 seconds. Which was bigger than our TA, and that was equal to 0.56 seconds. California has a... Okay, we're going to move to step number 6, which is calculating seismic response coefficient CS. If we go into, let me bring it up here, if I can find it. right here, this is what we're looking for, actually find V, but we finally gotta find CS. Seismic, and there are some limitation here. So there is, we gotta calculate method 2 first, and then make sure this is not more than that, and then we're gonna go ahead and make sure that we are within some certain boundary. So let's get to work. Remember, we already have these numbers, SD1 and T. T came out to be 0.56 second, and our SD1 came out, let me see the Excel here. We measure all this stuff from the, actually from here. We got all those numbers from here. So that's what we're going to use. All right. So this is equal, our SD1 came out to be 1.32. Divide that by T. T was 0.56 second. Time R. R came out to be 8 second. Divided by 1. And let me get my calculator. However, we're going to say the value CS should not be greater than the other equation that we saw, which was CS is equal, let me change color so they will not mix up, SDS divided by R divided by I, and our SDS is 152 divided by 8 divided by 1. 9. So this is controlling so far. If I did the calculation right, SDS. And also, so A 0.044 SDS IE. Let me bring. Okay, so basically we got to follow this rule right here. It's same section. We did this to this, and then it says right here, you have a lower bound for both method. It cannot be less than this, or 0.01. So let's go back to our writing, and that was IE 0.00 SDIE, and that is 0.0044 SDS. Our SDS is 152, and that's equal time 1. Point 123. 0.066 or say 0.07. B could be 0.01. C it was 0.5 S1 times R divided by IE. So it's 0.5. Our S1 is 0.88 and 8 divided by 1. Okay, so C is 0.5 times S1. S1 came out to be 0.88 and divide that by 8 by 1, and that comes out to be, so out of this 3, and this is the largest one, and our number CS came out to be this one, 0.2, almost a 0.2, is 0.29. So this is the one that controls, and that's the one we're going to use. CS value 0.19 or 0.2. Okay, we're going to move to step 7. Step 7 is going to be a little bit long. It takes a lot of calculation. We've got to calculate the weight of the building on each floor. There is some ASCE talks about 12.7 about some limitation. You can read that. I can bring it up in a second. Hold on. Let me see if I can find it. So there's this limitation right here. It is the effective seismic weight. And then I come back up here. It says none of these apply to ours anyway at this point. So it's a good reading. You should take read this stuff. And another thing is, so now when we do that, the first thing we want to do, we want to find out the area of our roof. Let me go back to the Revit model. So this is 120 by, what is that? 120 by 69 plus 80 by 45. That's the area we're going to look at it. And let me go back to the writing. And I'm so quick, I already did that. So now we're going to set the area as 69 by 120 and comes out to this number right here. Then after we have that, the first thing we're going to do, we're going to calculate the weight of the roof, the slab roof, which is the area is 11,880 times 150 pound per cubic feet, and the concrete is a 9-inch thick. Divide that by 12, make it a 0.75. So now you got 1, 2 gone, and that's a square foot. That's it. That will give us, check my calculation. I might be off a little bit. I'm doing just one time. I'm not don't have a time to double check it. Square, no, that's a pound actually. Pound. So I'm going to come back into my Excel. Let's go back to the Excel right here. You got to start this Excel. Make yourself this table here. We start from a level, weight, height, kx, which is basically these two, multiply fx and v, and then we have the roof, 4 floor, 3, 2, 1, and the total. So while I'm going to come up here, I'm going to say the roof, and that's the number we just calculated right now. Came out the area, that came out to the pound. Again, this is the pound. This is just for my own calculation for now. Okay. So now let's go ahead and calculate the superimposed dead load for the roof was 10. That was 10. So we're going to use the same area. Multiply by 10 pound per square foot, and that will give us basically 11,800. So that become like that, and that's a pound. And I'm going to go back to my Excel, and this where I put this number right here, that right there. Then we're going to calculate, and the PowerPoint said there was a glass. I mean, okay, it says right here also some that blah blah blah. A glass curtain wall system is used and is 8 pounds per square foot. Okay, that's right. So we're going to go ahead and calculate that too. So that's 8 pounds. And it's got to be multiplied by all length. And fourth floor to the roof is only 10 feet tall. So it's going to be 8 pounds times, it's 120 on one side plus 69 plus 69 plus 80, right? No, 45 on both sides. 45 plus 80. That's basically if you perimeter of the building. That's the perimeter, which comes out to be 428 feet. So that's 8 pounds per square foot times that, and the height was 10 feet tall. And so glass comes out to be 37,440 pound. I think that's right, but anyway, so going back to the Excel, and I'm going to put that number here also. Next, we're going to calculate the column weight, beam weight, and a wall. Everything we got to calculate. Let's go to the column. The column, it's going to be, let's change color for the column. And we said the column is 20 inch by 20, so 20 by 20 divided by 144, 150 pound per cubic feet, and there was 38 each column. And that should come out to 15,833. Let me double check that number. Excel, and that's where this number came from. Let's do the beam. The beam, it's gonna be let's say the beam is 12 by let's just give the beam of 12 by 24. So beam, roof beam, which we're going to use the same for a floor beam, and that's going to be 24 by 12 divided by 144 times 150, and the average length says 21 feet. I'm just going to average it. I'm not going to do exact. You can do yours, and it's about 31 of them at 10-foot spacing. So that's going to come out at 195,300. Okay, and we go back to the Excel, and that's where 195 comes in. So let's put a wall around the building, and the wall weight, it's going to be 8-inch concrete. So we're going to say 8 divided by 12 times 150 pound per cubic feet, and the perimeter wall was 428 feet long. Okay, that's the perimeter of the building. So that's a pound per cubic feet. That's 1, 2, I need one more, and 10 feet tall. We talk about this in a little bit, and that came out to 428,000. A lot of time, the designer uses a 50%. Instead of using the entire wall length, they use half. I'm being conservative. I'm going to use all the entire wall. So now I'm going to come back in my Excel, and put the wall here, and then I got the total here. So I'm going to take this number. I'm going to say roof weight is equal this number. Let me type in equal this divided by 1,000 to make it a kip. Enter. So it came out to 2,031 kip. Let's make this to a, it's a weight estimate, so I'm going to go ahead and come up, format the cell, number, let's just make it 0. That's what. Let's do the typical from second to the fourth floor. This number is going to stay the same, so that's going to stay the same. Each floor going to have the same amount of concrete. Superimpose is different. Let's go ahead and calculate that. It said there was 30 for each floor and 10 for the roof. So now we're going to come back for the superimpose. We're going to say floor 2 to 4. And that's going to be superimpose that load. It's going to be equal. The area was 11,880 multiplied by 30 pounds per square foot. That gave us 356,400. Let's put that in there. Go back to the PowerPoint. I mean the Excel. So that became 356,400. Okay, next the glass is going to be the same. The beam is going to be the same. Column is going to be the same. So these two is going to, everything is going to be the same. Okay, let's total it. And this is equal this number divided by 1,000. Enter. Oh, what did we do wrong here? Let's do it again. Equal this number divided by 1,000. Enter. All right, and that's going to be from this, going to be the same to here. Well, didn't do it. 2369. 2369. Okay, now the first floor is going to be a little bit different because the height of this floor is 12 feet. So this is going to say floor 1. It's going to be the same. That's going to be the same here. Glass not going to be the same. It's going to be, that's time 12. So basically that's going to be you can calculate it yourself, see if you come up with. That's what I came out with. See if you can come out with the same number. The column, it's going to be time 12, which I didn't do it, so I'm going to basically say equal this number time parentheses 12 divided by 10. Enter. And beam is the same thing. They're gonna, actually there's no beam on the first floor, is there? Well, if there's a basement underneath it, so let's put this away, make it the same. on a footing anyway. Unless it's a slab-on grade, then you have to do a different calculation. And wall, it's going to be same thing. It's come out to all right, let's add this up. Like that. Okay, so this one is going to be equal this number divided by 1000. Enter. Let's sum this right here. So the total weight of the building is 11,700 kips. And now I'm going to say the height of the this was a 52. The height of this one was 42 and 32, 22, 12. Okay, then that's going to be here equal this number multiplied by this number. Enter. And let's grab this and bring it all the way down. All right. And let's add this also. Okay, I want to make all this here. Perfect. So now we have this. Let's do the f of x. All right, the next thing we're going to calculate the shear, base shear, which is the CS time do total weight of the building. So let's do, what I mean by that is if we go to the code itself, let's show you that. What we need to do is, I want to write these two down. Be patient with me. Need that. And we calculating V, we already did V. V is, what's up here someplace? Right here, we did that. So then we're going to go ahead and come calculate these two. What I mean by that, let's see the Excel sheet here. So our V basically is equal 0.19 times the total weight of the building. So that's our V. The next thing I want to do is have these two equations from the ASCE and find out f of x, which is a C of V x times V. And that's the individual one to put right here. But before I do that, I need to find out what is this right here, which already has Wi times Hi. We did that, Wi times Hi. The summation came out to be right there. Okay, now we got to write an equation to calculate the CVX. I'm going to make a column right here, call CVX. And that's equal the total weight, which is right here. No, I lied. Oh, we got to calculate K. So, okay, to calculate K, how do I go 1.03? Let me show you. Coming back in here it says for a structure that have a period between 0.5 and 2.5, just use linear interpolation. And let's go back to my Excel. I always have it in all my Excel, and you should have it too. Right there. No, that's not. Okay. So if I look at all my Excel calculation, I have this here. You should put them in there. This is the equation for linear interpolation. You just write a simple program, and there it is. And if you want to copy it, this is how you do it right there. Click on that, and there's my program right there. So we have a 0.5 is 1, 2.5 is 2, our was 0.56. So our K1 become 1.03. going back to our equation right here, so we're going to have W x times h by power 1.03. Let's see if I can make this work. Write an equation here. That's going to be equal. Might have to put a bunch of parentheses in. Hx is right here, and W is right there. So we're going to have W time Hx parentheses Hx right there by power 1.03, close the parentheses. Okay, I'm going to put another parenthesis around it here and put one at beginning also. I have a feeling Excel not going to be happy with me. And then divide this by summation, which is right here, and hit enter and cross your finger. Oh, came all right. Okay, so that's our CVX. So our FX, which is right here, is equal this number multiplied by V, which is right here, enter. We get 754. And let me just drag this, if we can do this all the way down here. Okay, so I fixed the Excel here. So I'm going to have CVX is right here. And that was basically this equation. I make HXK right here, so make it easy for my Excel. And then this was basically is height by power 1.03, and I drag it down and drag this one down, drag it down. Excel becoming a pain in the neck. So V is basically is going the opposite way. This is equal 754. This one is equal this number plus this number. Enter. And we're going to bring that all the way down to here, 2473. Okay, so this number and this number, they match. Let me just color them. And that's what we like to see. However, they should match this number here also. But the reason it didn't do it is because the way the Excel sometimes work, it just has like this, you know, how they round up and end up, and then also we use one linear interpolation and came out 1.03, but which is correct, but it should come out the same. Anyway, now we have this, and we're going to go ahead and draw this on our building, and then we take it to the next level. Okay, so our shear force in here, that's our V, which is came out summation equals summation of f of x, and our Excel came out to be 2473, and V is equal 2473, which came out to the summation of x, same number. And up here we have different number on each one of them, this one, this one, this one, this one, and that was from the Excel from the top to the bottom. This was 754. This one was well, I'm going to write right here, 754 and 673, and this one was 508, and the bottom was 346, and down here it's basically came out to be 192, and if we all that up, it should come out to this. And then we will take these number and apply to our design, which we're going to do in the next lecture, how we're going to design a shear wall with kips. So all these numbers are in kips. and then we can convert them to kips per foot or pound per foot when we do a shear wall design or any type of design. I hope you like this and enjoy it. Have a great weekend.